No! Okay, we're going to need for the tutorial now 2 hours, so we should get pretty far. I'm going to give a recap of the lecture of just now. Here we go. So, for everybody who doesn't like mathematics, and just wants to know what the physics was, here you go. We have a proton and or a neutron. Again, we're just looking at the nuclear force that doesn't distinguish between the two. There's a separation of R. The separation R only depends on the magnitude, not the direction, and as a result, what we got out was that the energy that these things have apiece is proportional to the zeros of the Bessel function. That was the whole lecture. That's yeah. But oh, there should be an alpha here. Excuse me. There we go. You know that these Bessel functions, they come with this order, right? This alpha value. For every alpha value, you get a different Bessel function. And our alpha, we saw, we abbreviated it before, was L plus 1 plus 1 over 4 square root. That was our order. Now, as a group exercise, what I would like to do is look up the zeros of these Bessel functions for different values of L. Now, we now have a number of variables that we have to deal with. One of them is this. You have this L value. Where did it come from? From the sphere of harmonics, the angular part of the solution. And what we saw before was L could have values, integer values. Why? Because of mathematics. Because mathematics tells you that this was the case. We also saw that there is an M value in between these two. Why? Because of mathematics. Question to you. What does this E depend on of these values?
What's the question?
The question is, we're going to find some energy numbers, right? Some values for the energy. And it depends on, well, M's, L's, something like that. It's key for what we're going to do next. So what does it depend on? Maybe I'm not asking my question clearly enough. If I change my value of L, does it change the value of the energy?
I guess so.
I would say yes. Because these are the zeros of the Bessel function. Which Bessel function? The one that has alpha here. Bessel functions come in all kinds of varieties. For every alpha value, you have a Bessel function. Yes?
I'm sorry to go back, but what do you mean by zeros of the Bessel function?
Bessel function is a function of R in our case. And if you would draw a Bessel function, they sort of look like sines, but not really. So they sort of look like this. So if you draw them as a function of R, here's a point where it goes to 0. Here's a point where it goes 0, 0, 0, 0. So what are these values? Those are the J's.
Okay.
Now for every Bessel function, here's a Bessel function with one particular value for A, alpha, excuse me. If I take another alpha, I will also get a Bessel function. It looks similar, but it just crosses the axis on different points. So for a different alpha, I get a different graph. I can also get different zeros. In other words, what these numbers are depend on alpha. This is why the alpha is here as an index. Alpha, in our case, depends on L. So if I change my L value, I change my energy. Here's another question. Suppose I've chosen my L value. And I choose within a certain L value, you have different M values too. Do those change the energy?
No.
I hear a couple of no's. That's the correct answer. Because my alpha value here, the thing that will change our energies, my alpha value does not depend on M. So that means that if I've chosen my L, doesn't matter how I choose my M, it will give you the same energy. How many different M values are there per L?
2L plus 1.
2L plus 1. Okay. here comes that was just mathematics, here comes a very important physical conclusion. That means that at the moment I've chosen my L value, I get an energy, or in other words, some energy level, some value. But in this energy value, I can put 2L plus 1 nucleons. Because every n value is another quantum state. It just so happens that these quantum states all have the same energy. That is a very important conclusion. It's so important I'm going to repeat myself just a second here. My energies, the energy levels that my nucleons will have, will only depend on L. That's what we'll get from the mathematics. My spherical harmonics also tell me that for every L there's a number of m's. But m doesn't change my energy. So for every L, I get this many energy levels with the same energy. So suppose that the energy that comes out if I take a certain L is 4 in some unit. Okay? Suppose this is the energy that goes with L is 2. Just as an example. We're going to do the full calculation in a second. So I take my L as 2, I do the math, and I find that the energy happens to be 4 in some unit. How many protons can I put in this energy level?
9.
You say 9? Okay.
18 then.
I hear slightly different answers. 9 is 18. Well, first, let's discuss the spins. Let's first convince ourselves that if I've chosen my L, and L is 2, I have 2L plus 1 m values. So it's 2 times L is 4, plus 1 is 5. Yes?
Yeah.
So in this level L is 2, there's 5 different m values. And every m value is allowed to have a proton or a neutron in there. So this one is allowed to have 5 protons. It also is allowed to have 5 neutrons, regardless of these 5 protons. And I'm slightly lying now. My claim is that there can be 10 protons and 10 neutrons in this energy level. Why is that?
Because of different spins.
Because of the spins. Because protons come and spin up and spin down. So what we have here is that for every energy level, we can not only calculate what the value is of the energy level, we can also calculate how many protons and neutrons will fit in that energy level. You're confused.
Why 5 and 5? Because it's L from 0 to 4 and then times 2 as well.
It is L2.
Oh, L2.
And L2 comes with 2L plus 1 m values, which is 5.
Sorry, just one
Yes.
question before we go ahead. What's the form? The axis? Because I
Oh, just some random energy
It's just
value.
one.
Yeah.
It's, yeah.
No, don't pay attention to the actual number. Yes.
Both
Yes.
When you use the same logic for electron orbitals, you often say that a certain L term, so for example L equals 2 is degenerate.
Exactly. That's exactly the same thing. In fact, those words I was just about to drop. This phenomenon that we now have, that mathematics tells you that there's different quantum states, because for every L and every m, it's another quantum mechanically, it's another thing, it's a different thing, but they do come with the same energies. This is called degeneracy in quantum mechanics, in case if you feel like looking it up. The fact that there's multiple states with the same energy, it's called degeneracy. What we're discussing now is degeneracy. Alright, so here's the plan. And again, it's a group effort, so we're going to do this all together.
Question.
Yes.
Could it be 5? It always has to be 5-5, or could it also be like 10-0?
No, it has to be 5-5.
Okay.
Because the fermions and the Pauli exclusion principle tells you that there's only so many you can put in there.
Oh yeah, of course.
So a proton and neutron, they can live happily together because they're not the same particle. Not so much protons and protons. Okay. Group efforts. What we're going to write here now is energy. This is the energy axis, all the way up here. And my plan is to find all the energy levels. We know that they are discrete. You cannot have any energy. It's only certain amounts of energy, which is this number. Now, there's a number in front here. And if you go back to the other room and you look at the board, you see that you can calculate what this number is. It's not important for our argument. The only thing that we need to know to see what the magic numbers are is how much space is there in between energy levels. Well, there's going to be a lot of space in between energy levels regardless whether there's a factor 4 in between or a factor 6. So for our question, what the actual magic numbers are, we don't care about this number. We only care about how far the energy levels are spaced. So let's forget about this number in front. If you want, you can calculate using what we saw before. We don't need it. I'm going to make a table. Does anyone have a phone, laptop, and find some website or a table or anything that we can find the zeros of a Bessel function? Because that's what we're going to need. I looked them up myself before the beginning of this lecture. Looked them up last night. Then I found that I made a mistake in looking them up, so we have to do it from scratch. This is not me joking, I actually made a mistake, so we have to do it right here.
Let's see.
Alright, we're going to do this for different kinds of L. So my listing, we're going to make a list here and then turn this list into a graph. Let's start with L is 0. What is my alpha for this case?
Root of 5/5.
It's the square root of 1/4. So it's 1/2.
Ah, yeah.
I found a table, but it doesn't give me integers.
Non-integers, you mean, or?
Yeah.
Okay, what I found when I looked them up, I found this website that gave me just a Bessel function 0 calculator. You could write on which alpha you wanted to see, regardless of which one. Do you have it?
Just
Yeah?
use Mathematica.
Okay, that's what Bessel function 0 calculator.com or something like that. These things exist. Somebody programmed this.
Oh, it's Casio.com. Something.
Okay, well, the good people at Casio. We should send a thank you note later.
Okay. I can fill in the order and the ordinal one.
Okay, so the order is what we call this alpha. And for L is 0, our physics L is 0 corresponds to our order of Bessel of 1/2. So could you fill that in?
Okay. Order of 1/2.
Yes. So what we have now is that this thing sort of looks like this.
And the ordinal numbers.
Yes, order numbers are just which 0 do you want, because they go through there's an infinite amount of zeros, and which one do we want? Let's take the first 5.
Okay.
So I'm going to write now the zeros of this Bessel function of order 1/2, and let's take the first 5 of them or so.
Why do you discard the negative values of alpha? Or they're just not mathematical solutions?
That is a good question. I have to think about it for a moment. There is something with Bessel functions that
Maybe they're even. Oh, actually, if they're
well, we have to look it up.
no,
for
but
a
then
second,
there'd just be
but,
2 times.
There is this rule about Bessel function. If you take the negative, that you sort of that is not linearly independent of your original one. So it's just a constant factor times your original. So J alpha is some factor times J minus alpha. So that means it's not a new solution. So the minus ones are really just the other ones with a different factor in front that we were free to choose anyway. It was sort of the argument sort of like that. We have to look it up to be sure. By the way, maybe we can make this even more of a group effort. So if, apparently it's Casio.com. Because we're going to need a whole listing. Can somebody please tell me?
Yeah.
There you go.
Let's try doing this in Mathematica.
Yeah, that's what I do usually. That's what I do usually. For people who happen to have Mathematica on their laptops, and I do. But do you? I mean, it's part of your. I mean, you know, Mathematica. It's this mathematics program. It's really big.
Wolfram Alpha.
Yeah, that's the one. And
Wolfram Alpha is online though. This is like
yes,
whole
and it
program.
actually has a function that's called Bessel zeros or something like that. Yes. Because listen, we're going to need all these zeros here. Yes. So if we're going to wait for one person looking this up, it's going to take some time. Okay, this we can all do. Not use Mathematica. What is L is 1? Which alpha value is that? 2, 1, 2, 2, 1, 4, 2. Okay.
13 over 4.
think this one.
Yeah.
Okay.
And the next one is 3 to 6, 6 times 25. So, oh, look at that. Now look at this sequence.
All squares.
So the first one is
This one?
3.14159.
You know what? Would you mind writing them down?
3 point.
Who was doing some other ones?
So not make 5.
Yeah?
Yeah, if you want to like,
Just take one, who cares?
But
Just try
First meeting the other ones as well. Look, this is fine.
Yeah, that's exactly what I was saying. It's exactly.
Because when I did it, I also found it.
I'm surprised too.
But like five digits or 5 values, the first 5
The
values.
word, just let's say the first 5 values. We don't care about the digits. Okay, this is good.
So like,
the first 5.
Jeff, you can just read that. I will write.
Okay, so
1 point.
we can also write a code that does
No,
it.
the first one for
What
1.5.
take your iPad,
It's
He wants you to write it on the board.
bodily remove yourself this.
Sure.
No, it's just there's more numbers than the two of us have hands. So
Oh, right.
Oh, okay, smart.
Which for which one?
Oh, probably.
For the next one,
For always, no, but always do, sorry, I don't know your name actually.
Wait.
Arsalan, Arsi.
Oh, that's too close.
And
Too close.
Nice
Pleasure
to
to
meet
meet you.
No,
For
just
3 half.
like we need the 5 zeros for the
Oh, all of them.
alpha
So
half.
4.49.
4.49.
I'm so sorry, I got carried
No,
away.
no, don't worry. I understood the digit. No.
5.76.
5.76.
Does that mean something?
How high do you want us to go?
5
first one's
5 zeros.
Okay.
yes, the first one is
So
mine.
Is that-
6 point.
Yes,
I'm
that's
so
not
sorry.
coincidence. You
I'm
can-
so sorry. All of that is wrong.
You can
All of
write
that
the
is
Bessel
wrong.
function as a combination
Even 3.46.
No, the first one is right.
Okay, nice, nice.
I'm so sorry. The second one is 6.28.
Extension of
Ah,
factorial.
it's just it's factors of that.
3
Yeah,
times 2.
9.42.
How do you make a factorial out of, say, 1/2?
yeah, factors of n. Yeah,
12.57.
It's called the gamma function.
yeah.
Okay.
And
Hey,
the
sorry,
gamma
five-
function, it so
12.58,
happens is directly
six.
related to
5.7.
pi.
7.
If you take non-integer factorials.
15.71.
15.71.
Of 1/2 is square root of pi. Don't ask me why.
Yeah.
It comes out of this thing. So the fact that you have Bessel functions now, which can be written if they're non-integer
Sorry.
as
No, I
gamma
can send you
functions,
the
and
ones,
non-integer
for
gamma
the
functions are
five
related to pi.
For 5
It's
half.
not the same
Yeah.
that pi comes out. And look.
Wait, let me just write a
In
code
fact,
that
what we
does
see
this.
here
So that we don't
now
have
is
to.
that 1/2, this is for everybody, it's interesting, that the zeros of this Bessel function with order 1/2 is always multiple times of pi. That is not a coincidence.
Okay. Coincidence.
It is, no, this is,
I think
Yeah,
not.
because it's like a sine function. No?
it is, but that's a little bit too easy. The reason I just gave a second ago is that the Bessel functions can be written as gamma functions. The gamma functions are an extension of factorials. The factorials of half integers are related to pi. And apparently it's exactly pi in this case. Okay, we're getting there. This is enough. We only need 5 of them or so. Okay, we're getting there.
Should we do these as well?
Yeah.
Yes,
I'll do
actually,
5.
yes.
Total
halves.
7.
Yes, I'm just writing a code. Okay.
Someone can do 9 halves.
Okay, here's all of them now. So now we want for 3 halves, you said?
Yeah,
Or 5 halves.
5 halves, yeah.
Okay. 5.76.
This calculator is really slow.
Yeah, and that's the one
9
that I use too. It takes 5 seconds or so before it gives you one answer.
9.10.
But in that sense, it's nice that mathematically it has an actual built-in
12.32.
Bessel zeros or something like that.
Yeah.
Gives you answers immediately.
15.51. 18.69. 7 halves?
Yeah. No, 9 halves.
9 halves?
No, 7 halves.
I'm doing 7.
Oh, okay.
Okay. 8.18.
Yeah. 8 point, sorry?
18.
1
11.70. 15.04.
Yeah.
18.30.
Yeah.
21.53.
18.30.
Yeah.
And
21.53.
Okay. We almost got them all. This is starting from this is the first one?
starting from the back.
Oh, you're starting from the back. Okay. The fifth one first. Let me see. Okay. Yeah, don't worry too much about the big number of digits, because ultimately what we're just going to do is see which energy levels are closely grouped together, and that will be the case regardless whether you or not you take the fourth digit.
Because you can fit 5 protons. No.
No,
Why do you use 5?
No, the 5 you just made up. That was just
Okay,
as an example.
Mhm.
Okay, we have the actual numbers now. Here's a good question. No, just skip the question just for now. Let's work with this for a second. We have the numbers right here. Now, if you take these numbers squared, because that's what you need to do to get the energies, you get up to some factor you get the energies. Now so pretty much what we have here, except for one square, is sort of the measure of the energies. Okay, let's start with the lowest energy. What is the lowest energy that will come out? Not the number, but which of these numbers correspond to that?
Sure, half.
Yes, this one. The first zero of this Bessel function. Alright? So some number comes out. I don't know what the number is. You have to square this pi squared, multiply with this other number that we don't know right now. We don't need it for our argument. Some number here. So this is L is 1 and L is 0. This one. How many n values does this level have?
3.
Sorry, maybe?
1.
3.
L is 0.
1. M tabel is 0.
Yes, M0.
Oh, yeah.
Yes. Here's the formula. Yes.
Yeah.
Or you can just see it here. I mean, if L is 0 and L minus L is also 0, then M can only be 0 itself. Okay, so how many actual energies can you put into it? They're all the same value. It's all this one value that you get here. I don't know what the number is, but some number. How many particles can you put in here? How many states are there?
2.
There's 2. There's 1, because L0, M0. And you can put 2 spins in there, spin up, spin down. So you can squeeze either 2 protons or 2 neutrons, or 2 protons and 2 neutrons. Alright, so that's this. Let me write it just here. 2 times. This is called the degeneracy, how many particles you can put in there and have them having the same energy. Okay? Which one is the next? This one we've done.
2 3/2.
Yeah, this one's pretty good. I agree. So this one corresponds to L is 1, yes? Agreed?
Yeah.
And how many particles can you put into there?
6.
6. Because M, in this case, can have 3 values. 3 values. And because of spin up, spin down, the total number is 6. There's a gap here. That gap is, which one is it? Is this gap. You see some magic numbers.
2 plus 6.
Yes. Putting nucleons in, if you just go to this level, you can put 2 in. Right? If you keep on filling, then Pauli principle tells you that the next ones have to go in this one. But there's a gap. It will cost you more energy to put them in. But you can fill it up too. In total, there's 8. Second magic number. Let's continue. What is the next one that we can have? By the way, yeah, okay. Which is the next one? Energy-wise. We're going to have another gap. Which one is it?
Half, but the 6.28.
This one?
Oh, I didn't see that, yeah.
Right. So there's another one that corresponds to L is 2. How many particles?
12.
That will be 12. 12 particles. Still agree?
10 particles?
Yeah.
Why 10?
Magic number is 20, yeah.
No. That's what you want. That's what you wanted. That's what you wanted to come out.
Yes.
Oh, yeah, no.
Because there's 5.
No, that's not how you do physics. Okay?
I know the answer.
Okay, let's count. 2, 5, 2 times 10. Okay. Oh, wait a minute. That sucks. That's not a magic number.
No.
No. Okay, no, we have this one. But look at this. These are pretty similar, right? They're not exactly the same number, but they're close.
Yeah.
So very close to this one, much close. These two are much closer to each other than these are. Is that one over there, which corresponds to L is 1. How many particles can you put into this one? 2. Because this is L is 1.
Or L is 0.
What's that?
L is 0.
L is 0. You don't.
Yeah, it is 0.
Yeah.
Oh yeah, excuse me. Yes, you're right.
And so you can get to it.
Yes. Okay.
Everything else.
Yeah. Oh, you could have put in 6, yeah.
All right. Are there any more that are close in this group? Any more particles that are close? I mean, this energy level and this one are pretty. This one and that one are pretty similar, but
The 699 is closer to the, I don't know, to the 7.7, yeah.
well, these two are pretty close together, I guess.
Yeah, I think they're closer, yeah.
So there's a gap. It's a
Mhm.
gap. It's a small gap,
Yeah.
but there is a gap. These two, this one, that one, and that one, are closer together than the next one, the next group. So this one is L is, which one is it? This L is 3, how many particles? 3, 6, 7, 14, 14. 14 times, that's that one. And this one is close-ish. So this one, where was it? This one is next. This L is 1, how many particles? That's 6, including the spins. And look at this, 699, 772. Close-ish, yes? Let's see, but the L is 3, that was 699, the L is 1, it's this. How do I get the L is 1? I feel that. 699.
I think it's 7.72.
Yeah, that's the one, yes.
Yeah.
And is it all close-ish? 8.18?
Yeah.
Sure. It's probably very close to. And that's 4, so how many particles there? 4, 8, 9, 18.
18. Yeah.
18, yes.
Mhm.
And I think then the next step from 8.18 to the next one, 9.10, they're all close-ish. Okay, let's stop here for a second. What we've seen here is that there are really distinct gaps between some of these energy levels that are grouped together. This one is really just by itself. This one, 3.14 and 4.49 are really far away from each other. That's like 50% difference or so between the two. So that's a big gap. So that means that if you are nucleons and you try to squeeze together nucleons, then this only takes putting two together, these two, is very easy. Try to add another one, all of a sudden costs you this extra gap of energy. It becomes much more difficult to do that. So apparently, grouping 2 together is much easier than grouping 3 together. That's exactly what we mean by a magic number. 2 grouped together cost less energy than grouping 3 together. And by less, I mean really with a small gap in between, with a big gap in between. Here's our first magic number. There you go. Now, okay, once you've made the sacrifice of adding more energy, then you find that grouping 6 together with an extra energy, that is easy. The 7 all of a sudden requires another big gap. So apparently grouping apart from this to an additional 6 costs less energy than trying to add another particle, because then you have to jump another gap. So apparently this number of particles, which is 2, is a magic number. Costs relatively low energy. And then adding extra particles, so you get all the way up to here, in total gives you 8 nucleons that are relatively easily put together. That's the second magic number. If you go to this one, the next one, this next group, It's 10, 12, plus this is 20. That's the third magic number. We're getting our magic numbers back, the one that you could just measure experimentally. From this point on, it becomes sloppy because the energy levels all of a sudden are not that clearly spaced out anymore. So it's sort of arbitrary if you consider this a group or not a group and whether you find the gap big enough. This is the part that one of the big exercises is going to be for this week, to figure out if you add Coulomb propulsion, if the sequence becomes better. It's a big exercise, it will take time. Yes?
Is this also related to the electron orbitals?
Yes, in fact, well, I just jumped right into to give the answer, but maybe I should give you a second to explain what you mean.
Well, with like 2s and 2d and those kind of...
Yes. In fact, it's extremely similar. We've now solved the Schrödinger equation for the nucleons in the nucleus. Forget about the nuclei for a second. If you try to solve the Schrödinger equation for electrons around the nucleus, the Schrödinger equation looks different because of the different potential. You have the Coulomb potential, not this potential that we use. So the mathematics becomes, the solutions become different, but the mathematics, the style of mathematics is the same. You solve the Schrödinger equation, you look at where the energy gaps are, and then you find that it's energetically much more favorable to put 2 electrons close, and then an additional 8 in the next orbit. And then you get the inert gases, right? Helium, xenon, what are the other ones?
Neon,
I forget krypton, those ones. And from chemistry, physical chemistry, you know that these are atoms of which the electron configuration is energetically favorable. Or equivalently put, that it's very difficult to get one of these energetically favorable atom configurations, electron configurations, to let it combine with another one to make a molecule, because they're already energetically favorable by themselves. They don't need another atom to find something even more energetically favorable. This is why inert gases are inert. They stay the way that they are. Or another way of saying exactly the same thing, the energy levels for the atoms, for the electrons, are completely filled. That's exactly what we're doing here. The magic numbers in nuclear physics are exactly what the orbitals are in atomic physics. It's just that the mathematics is somewhat different, but the idea is the same. So it's extremely similar. Okay, so that's good. We found the sequence that I promised we would do. We found the first 3, and after that it starts to break down. Takes a while. But look at the beauty of this. No, really, I'm not joking. Look at the beauty that you start out with this quantum mechanics that we defined last week. We started with 4 postulates. We got this quantum mechanics out. We use this quantum mechanics, do the mathematics, all of a sudden you can predict all kinds of nuclear properties. So that's nice. So I think we're making progress. Any questions so far?
You know, you said like it's easy to group 2 together, and it's also relatively easy to group 6.
Yes.
But it still takes less energy to group 3. It's just not stable, or is it that the energy it will take more to group 3? You know what I mean?
Yeah, I know what you mean. Of course, it will take less energy to group 3 together.
Okay.
Of course, because now you only have to take one of them to this next group of ones.
Oh, okay.
Yes.
I see.